Okay, so we're in 16.8 now. We're talking about a theorem called Stokes Theorem. And before we get too far into this, I wanted to give a little bit of background on this. So the theorem that we're calling Stokes Theorem here to a mathematician is actually called the Kelvin-Stokes Theorem. The modern mathematician would refer to Stokes' theorem as a huge generalization of this. In fact, the modern version of Stokes' theorem is a theorem in differential geometry, a very advanced, very interesting area of mathematics. This is the theorem that this is the version of that theorem that was proven originally, and it wasn't until much later that it was generalized to the theorem that you would see if you were to look this up on Wikipedia or something like that. The name Stokes theorem also comes from a mathematician named George Stokes, and it shouldn't really be called Stokes theorem in my opinion because he wasn't the one that proved it. It was proven by a mathematician who went by the name of Lord Kelvin back in the 1800s, and he communicated this proof to George Stokes, which is why it ends up with Stokes' name on it. It's a weird thing about naming theorems in mathematics in the past few centuries. Sometimes the names that get attached to theorems don't actually indicate what they seem to indicate. But anyways, that's just a little bit of background. To us, this is going to be called Stokes theorem, and that's all that we need to really know. So let's get into it. S is going to be an oriented piecewise smooth surface, and it's going to be bounded by a simple closed piecewise smooth boundary curve C with positive orientation. So before we read the rest of this, here's an image of what we're talking about. The surface S is just an oriented surface. You notice in this case it's oriented upwards, so we would call that a positive orientation for that surface. And that's indicated by these normal vectors here. But the boundary curve C is going to be positively oriented in this theorem. So again, if you could see this picture, it's a little guy kind of walking along the boundary curve C, and the curve remains to his left. If you remember, that's what we call a positive orientation for a simple closed curve. And notice also C represents a boundary of sorts for this surface C. Okay. If F is a vector field whose components have continuous partial derivatives on an open region in R3 that contains S, then we have this theorem, which we call Stokes' theorem. It relates a line integral to a surface integral. It says the line integral along the boundary curve C that we defined up here, so this curve C, of f dot dr is equal to the surface integral over S, so the surface that C is acting as a boundary for, of the curl of f dot ds. Okay, so let's quickly take a look at what each of these represent. So remember, the line integral of f dot dr along C is the same thing as this. The line integral of f dot t ds along C, we call that the line integral of f along C, or the line integral of the tangential component of f along C, because that's what this is. F dot t is a tangential component of our vector field f. The curl, what we had done in the previous section, the surface integral, if this is any vector field in here, curl of f is just the vector field we happen to be talking about, is the same thing as the surface integral over S of the curl of f dot n. So this is the normal component of this vector field. Okay, so it's relating the line integral of the tangential component of the boundary surface to the surface integral of the normal component of the curl of f. I know that's a lot, that's kind of a mouthful, but that's sort of trying to put that in some terminology that we've seen before. If you want to look at a special case of this, let's suppose for a second the surface S is in the xy plane. What does that tell us about well, first of all, the curl of f would also be in the xy plane. Remember, when we talk about the curl of f, we're talking about, if we want to evaluate the curl of f, and f is a surface in the xy plane, then the k component of that would be 0. And the result of that, which we've seen before, is that the normal vector is going to be pointing in the direction of the z-axis. It's pointing up from the xy plane. So that means that the normal vector of a surface in the xy plane is just k. That's the k vector, the unit vector k. So what that means is that in the event, or in the case of Stokes' theorem, the line integral of that along that boundary curve of f dot dr is equal to the surface integral of the curl of f dot ds. That's the theorem. But when you evaluate this curl, remember it's the curl of f dot n, the unit normal, and the unit normal in this case is k. So this becomes the surface integral of the curl of f dot k dA. This is Green's theorem. Remember, this is the vector form of Green's theorem. So basically what this says is that Green's theorem, really, really important theorem for us, is actually just a special case of Stokes' theorem. Stokes' theorem is a more powerful generalization of that theorem. Okay, so with all that said, we're going to launch into a proof here. This is the proof. It comes straight out of your book, and I'm basically just going to walk you through it to help you make sense of what's going on here. You'll see in there that we can't, within the scope of this text that we're using, we can't prove the most general case of Stokes' theorem, so we're going to make some assumptions here about the surface S. We're going to assume that S is the surface that comes from an equation of the form z equals g of xy. Okay, so we've seen that this leads to some useful formulas if the surface is actually the graph of a function. So we're also going to assume that g, this function that defines our equation here, z equals g of xy, has continuous second order partial derivatives, and we're going to assume that D is a simple plane region whose boundary curve C1 corresponds to C. So basically what that means, if I look at my picture up here, this surface looks like it could be the graph of a function. And what it's describing is this plane region here, whose boundary curve is C1, and the plane region is being called D. Okay, so when you see C1 and D in this proof, it's talking about the projection of this thing into the xy plane, so that we think of this region D as the domain, or the part of the domain of the function that gives us this surface up here. Okay, so that's what that's talking about. Okay, if the orientation of S is upward, and you notice that that's the case here, then the positive orientation of C corresponds to the positive orientation of C1. In other words, if C1 is oriented positively here, then C is oriented positively as well. The positive orientation of the surface doesn't cause a reversal of the direction of that, or of that orientation. Okay, we're also given that the vector field F in component form, we're going to write pi plus qj plus rk, and we're given that the partial derivatives of p, q, and r are all continuous. All right, so if you recall, in section 16.7, so the previous section, we said that there's a useful formula that we can use if you want to find the surface integral of a vector field that's given as a function of x and y. And it's this. Let's see if I can sneak this in here. The surface integral of f dot ds in that particular case can be evaluated this way. Negative p partial of z with respect to x minus q partial of z with respect to y plus r dA. Okay, we went over that theorem. We didn't use it in an example when we talked about surface integrals, but we showed that this is a special case of when the surface S is a function. We're going to use this a couple of times. So in this case here, the the P, Q, and R that I'm talking about are specifically going to not correspond to the vector field f, but to the curl of f. Remember, the curl of f is a vector field where these, in the parentheses, these are the I, j, and k components. So substituting p, q, and r, I'm substituting these three components for the curl of f. And notice it starts to look very, very messy, but that's okay. So now the next thing, it mentions the partial derivatives of p, q, and r are evaluated at particular points on the surface S. So if we have this parametrization for the plane curve C1, x equals x of t, y equals y of t, and t ranges from a to b, then we know that when you parametrize a surface, that's the graph of a function, the I and j components, or the x and y parameterizations, are borrowed from that plane curve, and then z is just equal to the function that defines it of x of t, y of t, and we use the same interval for our parameter. T goes from a to b. This is giving me a parameterization of C, the boundary curve on that surface. Okay? So here's where we get this kind of lengthy and somewhat messy looking proof. What we want to do, let's go back to this. Remember, we're trying to prove Stokes theorem, and basically what we're trying to do is to show that these two integrals are equal to the same thing. What we've already done is come up with an expression for the right-hand side, the surface integral over S of the curl of f dot ds. That's this messy-looking thing. Okay. My goal now is to take the line integral of the space curve C, the boundary of S here, of f dot dr, and show that it comes out to the same thing that the curl, or the surface integral of my curl of f dot ds came out to. That would show that they're equal to each other. So we've worked on the right-hand side, we're now working on the left-hand side. Okay, what does that look like? If I want to take the line integral along C of f dot dr, first of all, remember we defined f to be pi plus qj plus rk, and dr, with the parameterization that we just came up with, looks like px dt, py dt, or sorry, dx dt, dy dt, dz dt. So this is what that dot product would look like, and we've seen this before. We already should be familiar with this. Now, remember, we're specifically assuming that z is a function of x and y for this special case of the proof of the Stokes theorem. In particular, z is a function of x and y, and each of those are functions of t. So when I'm talking about z of t, I can use the chain rule, the multivariable chain rule, to expand that to this. This comes straight from our chain rule right here. Okay? Now, if I were to distribute r, remember r is not a constant, it's a function. It's one of the components of my vector field f. If I distributed that and then combined some like terms, I'll notice that each of my terms contains either a dx dt or a dy dt. We see the dx dt and the dy dt showing up here. If I group the dx dt terms, and if I group the dy dt terms, and then factor out the dx dt and dy dt, I end up with this. Okay? Yeah, okay. So now this particular definite integral is the same thing as this line integral, where if you notice the curve now is C1, and the dx dt, remember, that becomes a dx. The dy dt becomes a dy. You can sort of informally think of distributing this dt in and canceling those dt's out there. But this is one of those types of line integrals that are have a dx and a dy in them. Okay, this shows up, this type of line integral shows up in Green's theorem. We know that because we're talking about something in a plane, we're talking about a curve in the plane. So this is now down in R2, if you think of it that way. So we can apply Green's theorem to this to give us a double integral over the region D that C1 is the boundary of, and Green's theorem leads to this. Remember, the partial of the second function here with respect to x minus the partial of this first function with respect to y. So that's what this becomes, okay? Now, you'll see this is straight out of your book. It says then using the chain rule again and remembering that p, q, and r are functions of x, y, and z, and that z itself is a function of f of x and y, we get this. Now this is a very, very messy integrand, but basically, without walking through every single little step here, what it's saying is that if I take the partial derivative of this guy with respect to x, it expands way out into this thing. And again, this is actually just an application of the chain rule to a couple of these functions here. Notice we also have a product rule to worry about here. So this first set of parentheses becomes this whole thing, second set of parentheses becomes this whole thing. Now your book mentions this, and I'm going to let you verify where this is occurring, but you get a lot of cancellation here. You need Clairaut's theorem, and that's why we assume that this thing has continuous partial derivatives, is because that's what allows us to use Clairaut's theorem. But you'll notice, for example, like the r partial of z with respect to y then x, and here I have r times the partial of z with respect to x then y. Clairaut's theorem says that these two things are equal to each other, but notice there's subtraction happening here, so these cancel out. You get cancellation of 4 terms in this great big double integral here. Now notice this is a double integral over the region D, and back here when we looked at the curl, we also had a double integral of the region over the region D. And it turns out that after the cancellation of those 4 terms in this integrand, and doing a little simplification, you can get this from this. Okay, and I'm not going to go through all the work to show you all the cancellation and everything, but it's a good exercise just to. It's not complicated. It's just a lot of writing. It's a good exercise to convince yourself that those two things are equal to each other. So that establishes that the line integral along C of f dot dr is equal to that surface integral over S of curl of f dot ds. Okay? So, I know that's a lengthy and kind of messy proof. Let's do a couple of examples where we're using Stokes' theorem. You'll notice if you read through this section, it's actually not a super long section, really just a couple of examples, and then we're going to do a couple of conceptual things at the end of this. But let's start with this. I'd like to evaluate the surface integral along S of the curl of f dot ds, where f is this vector field. Kind of a messy looking vector field. Not the worst thing in the world, but not terribly pretty. So S is going to be the cone x equals the square root of y squared plus z squared, where x goes from 0 to 2, and it's going to be oriented in the direction of the positive x-axis. We're not going to really use that orientation explicitly here, but what I want to do is start by sketching this surface. Okay, so it's a cone, but notice the form, it's not z equals, it's x equals. This will be centered on the x-axis. So let's say that this is 2 out here. This would go to the origin. Probably could have drawn that a little bit differently. So that's a cone. You can't really see the point of it very well the way that I drew it. Okay, but if you consider this circle, the circle that is contained in the plane x equals 2 is going to be a circle of radius 2. So if I wanted to come up with an equation for that circle, it would look like y squared plus z squared equals 4, and x is equal to 2. Okay, so we need a parametrization for this curve. Now this curve is what's acting as like that boundary for our surface. And notice the cone does not contain the base here. It's just the outside. I don't know what you would call that, the slanted part of the cone. So let's start with the parametrization. R of t, and this is for my boundary curve C. R of t, x is equal to 2, so that would be 2i. And then y and z go together to make a circle. So we use the standard parametrization for a circle of radius 2. 2 cosine of t j plus 2 sine of t k. Now notice what it's asking me for. The double integral, the surface integral of the curl of f dot ds. if I evaluated this directly as a surface integral, it gets really not fun with this vector field that I'm working with. And the fact that this is showing up in the theorem section on Stokes theorem implies that we should be using Stokes theorem somehow. Well, again, Stokes theorem says if we want to find the surface integral over s of curl of f dot ds, then I can use a line integral instead of f dot dr along the boundary curve of s. So that's nice because what we just did is parametrize that boundary curve. And this is leading me towards finding that that line integral that this will be equal to according to Stokes theorem. So it's f dot dr that we're going to use. I need my dr, which remember comes from just the derivative of this. That's going to go to 0. I'm going to get -2 sine of t j here plus 2 cosine of t k here. That's my dr. All right, now in order to do f dot dr, remember by f, what we really mean in that line integral is f of r of t. Okay, so I need to substitute this parametrization in to my vector field f. If I do that, you can verify this. Inverse tangent of x squared y z squared. That's 2 squared times 2 cosine of t times quantity 2 sine of t squared. All of that, after doing some simplification, comes out to 32 cosine of t sine squared of t. That's my I component there. Okay, plus x squared y. So let's see, x squared would be 4, y would be 2 cosine of t. 4 times that is going to give me 8 cosine of t, and that's my j component there. And then finally, x squared z squared. That's going to be 4 times 4 sine squared. That's 16 sine squared of t. Okay. Okay. Next thing I need is f dot dr. That's what I'm going to use in my line integral, where here's dr, here's f. Conveniently, my dr has a 0 for its I component. Notice the I is not present here. So this complicated looking I component for f is just going to be multiplied by 0 in my dot product, and it's going to go away. That leaves me with -2 sine of t times 8 cosine of t, giving me -16 sine of t cosine of t plus multiply the k components, 2 cosine of t times 16 sine squared of t. That would be 32 cosine of t sine squared of t. Okay, this is the f dot dr. This is the thing that I'm taking my line integral of. Well, one thing I forgot to do also, remember this is a full circle, so I do need to set a parameter interval. T is going to go from 0 to 2 pi to complete that entire circle. All right, so now in order to evaluate the double integral, or sorry, the surface integral, I keep calling it a double integral, is the surface integral, of the curl of f dot ds, according to Stokes' theorem, that's equal to the line integral along C of that boundary curve of f dot dr. I have f dot dr evaluated here, so I can convert this to a definite integral. And notice my t goes from 0 to 2 pi. So 0 to 2 pi of -16 sine of t cosine of t plus 32 cosine of t sine squared of t dt. This isn't difficult to evaluate, but I'm gonna do something that's gonna actually make this even easier. Factor the cosine out. So this looks like the integral from 0 to 2 pi of -16 sine of t plus 32 sine squared of t cosine of t dt. Notice there's a natural u substitution to make here. So if I were to choose u equals sine of t, then du is equal to cosine of t dt. And this becomes -16u plus 32u squared du. That's not the interesting part. What's interesting is what happens to my limits of integration. If u is equal to sine of t, sine of 0 and sine of 2 pi are both equal to 0. So at this point, because I'm taking a definite integral and the lower and upper limits of integration are equal to each other, it doesn't matter what that integrand is. That's automatically 0. So all of this work, and we ended up with 0 as our result. Pretty cool. All right, so that's Stokes' theorem, which was used here, converting what would have been a very difficult surface integral into a less difficult line integral. Now, I'm not going to have time in this video to do the next example, but I'll set it up here. This example is going to be using Stokes' theorem in the other direction. So it's important to note this, that it's not always that we're evaluating a surface integral of the curl of some function ds. It's sometimes we're given this and we use the left-hand side to evaluate. Sometimes we're asked to do this and it's easier to use the right-hand side to evaluate. So the next example, that's what we're going to be doing.